Section 2.1 is going to cover two different ways of describing a location in a distribution. So the first is with percentiles, which we saw a bit earlier in Chapter 1 when we were talking about box plots and quartiles. So in this example, we have the scores of all 25 students in Mr. Pryor's statistics class. The bold score, which is noted right here, is Jenny's. How did she perform relative to her classmates? It's always good to graphically display any data set that we have. So here we have the box plot, and we see Jenny as that red dot right there. Now, a percentile is defined as the percent of data values in a distribution that are less than an individual's data value. So here we have our dot plot again. We have Jenny's score in red right there. If we wanted to find Jenny's percentile, we would count the number of values that are less than Jenny's score of 86. All right, if we add up all those dots there, we get 21. And since that's out of 25 students in the class, 21 out of 25 being less than her score, that puts her at the 84th percentile. Another thing to note is that percentiles are typically reported as whole numbers. So if we have something that ends up as a decimal, we're going to round it, and we're always going to round it down. Here's an example why. So let's say we have a data set with 43 values. What would an individual's percentile rank be if they're higher than 30 of the scores? So we put that into a fraction. 30 over 43 gives us 0.698. All right, now typically you would think that this would raise to 70, but remember the definition of percentile, okay? The percent of data values that are less than the value in question. And we don't have 70% that are less than this, so we would identify this as the 69th percentile. Again, we can't say it's the 70th percentile because there are not 70% of the values less than the 30th score. All right, let's do a few examples. And first off, we'll find the percentile for a student scoring a 72 on the test. So to start, we want to identify where that 72 is. It's going to be that point right there. And we're going to count up the number of values that are below that 72. And there's only one out of the 25, which would put it at the 4th percentile. Part B, if a student is at the 48th percentile, what was their score in the test? So now instead of finding the percentile for a given value, we're finding the given value from a percentile. So when it gives us a percentile like this, we're going to be working backwards. All right, and the key thing we have to know is how big is this data set? So we know that there are 25 items or 25 students in this class. So we want to find what is 48% of 25. Okay, we multiply those together, we get 12. And what that tells us is that the 48th percentile is higher than 12 of these 25 scores. So then we're just going to go ahead and we're going to count up from the bottom, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, those are the 12 that it's higher than, which means that value, 80, is the 48th percentile. Now, just to avoid any confusion, when there's small data sets, sometimes individual values can occupy a range of percentiles. For example, we just calculated that a student at the 48th percentile earned an 80 on the test. What's the median of this distribution? All right, on the last slide, we counted up all of these dots here. We found that there were 12. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so 12 to the right makes that value the median. So the same 80 that was the 48th percentile is also the median, which is the 50th percentile. That's not unusual considering this data set is only 25 students. All right, and we're splitting up those 100 percentiles across those 25 students. As data sets get larger, we'll have single values that'll occupy each individual percentile. Now, another way that we can identify the position of a data value within a distribution is with something called a z-score, also known as a standardized score. And what a z-score tells us is the distance a data value is from the mean measured in standard deviations. So here we have the equation for a z-score. On the top of this fraction, we're going to take our data value and we're going to subtract the mean. That difference gets divided by the standard deviation. And then over on the right here, we have the equation again, but this time with the symbols that we use for mean and standard deviation. We're going to see them more often as the year goes by. One of the most basic things to understand about z-scores is that values that are larger than the mean will have a positive z-score. Values lower than the mean will have a negative z-score. So that said, let's find the z-score for Jenny's test grade, which was an 86. Again, it's that red dot up there. And this time it gives us a table of summary statistics, including the mean and the standard deviation. All right, and those are the two values that we'll need to calculate the z-score. So we take our data value, Jenny's score of 86. We subtract the mean of 80, that's on the top of our fraction. And that difference gets divided by the standard deviation, and we get a z-score of 0.99. That tells us that Jenny's score on this test is 0.99 standard deviations above the average score. Now, since we're talking about test scores, we want our test score to have a z-score that's positive because that means we've done above average. If the z-score for a test was negative, that means we scored below the average of the class. And if it was 0 exactly, that means that our test grade was the same as the mean. Here we can see the original distribution of test scores. Right? Each score in this distribution has its own z-score, and that's what's displayed down here. Okay? We can see when we switch a distribution to z-scores, the shape stays the same. All right, the center is always going to shift to 0 because those 80s right here are equal to the mean. All right, so when we find their z-scores, we end up with z-scores of 0. And the spread gets thinner in this case. Okay, with z-scores, typically everything we see is within 3 standard deviations of the mean. Even to cross 2 standard deviations is somewhat unusual. All right, so standardizing a distribution equalizes its center and spread. Once we're talking about a z-score, it doesn't matter if we're talking about SAT scores, statistic test scores, heights, GPAs. They're all going to have a center of 0, and they'll have similar spreads. Now, one of the main reasons that we use z-scores is because it allows us to compare data values in different distributions. So, for example, Jordan was 55 inches tall when she was 9 years old. Zane was 58 inches tall when he was 11 years old. All right, so these are two children at different ages. All right, we know their heights. Obviously, the 11-year-old is taller, right? But who's relatively taller amongst their peers? So for that, we need a bunch of information about their individual distributions. So for 9-year-olds, 9-year-old girls, tells us the mean is 52.5, standard deviation is 2.5. For 11-year-old boys, that has a mean of 56.5, standard deviation of 3, right? Who is relatively taller compared to their peers. Now I have the key information summarized here, Jordan in black, Zane in blue. And what we want to do at this point is find z-scores for each of these children. So Jordan had a height of 55. We subtract that mean of 52.5 and divide by the standard deviation. Jordan's height has a z-score of 1.0. Zane, same thing, except this time we're using the mean for the 11-year-old boys, which is 56.5, and its standard deviation. All right, and we see that Zane has a z-score of 0.5. So based on those metrics, the farther a z-score is from 0, all right, the more unusual it is. All right, so since Jordan has a z-score of 1 compared to that 0.5 for Zane, right, Jordan is relatively taller because she's farther above the mean.